So this one. Hello. Hello, I'm Margot. I'm a PhD student from CNRM and INSA Toulouse, and I will present our work on the modeling of moisture transfer through walls at the urban scale. We take the example of an historical city center in the south of France. To give a little context, we are currently facing a climate emergency that requires us to enhance the energy efficiency of buildings. At the same time, cities are subject to the urban island phenomenon. And historical city centers are specifically vulnerable to this phenomenon due to the morphological complexity and high mineral content. One of the levers for reducing urban island is to retrofit building. To properly retrofit building, we have to consider the specificity, such as that old walls are made with highly permeable material. Applying unsuitable insulation can affect the moisture balance of the wall and lead to mold growth, for example. One of the solutions could be to retrofit with bio-based material which are highly hygroscopic and that preserve part of the wall permeability. Therefore, the objective will be to compare several scenarios, and for this we can we can use urban microclimate model, however, they are currently neglecting moisture transfer through wall. So we will work with the TEB model, Town Energy Balance. It is a multi-scale model. It can simulate street microclimate, the energy behavior of wall, and also heat transfer by conduction through wall, energy behavior of building. We will add the moisture transfer through wall in this model. The aim is to provide a comprehensive tool for simulating retrofit solution in historical city center. Before integrated moisture transfer in TEB, we have to better understand the main processes involved. Outside, the main phenomenon impacting moisture in the wall is the wind-driven rain, and under the effect of sun, evaporation can appear and lead to a local reduction of temperature. The wall also exchanges moisture with the indoor environment. Indoor conditions fluctuate with internal moisture gain and HVAC equipment. Some materials can help to regulate this fluctuation. This is a moisture buffering capacity. Moisture transfer also appears into the wall, and it can affect heat transfer by conduction. Indeed, moisture content in material can modify the thermal conductivity. And some points of the wall are particularly vulnerable to the accumulation of moisture and therefore to the mold growth. To take into account this phenomenon, we have chosen a new and one-dimensional coupled mass energy transfer. It is based on two equations, one for energy conservation and one for mass conservation. It leads to a system of two differential equations to solve. The method commonly used to solve them at the world scale are complex and based on fine spatiotemporal scales, discretization scales, making them unsuitable for the urban scale. So we developed an original method based on simple discretization and solution methods, and it works with coarser time step and meshes. It is suitable for the urban scale and easily integrable into TEB. This method has been validated by intermodal comparison. I will not present this method in detail here, but the result has already been published. Using this method, it was possible to integrate moisture transfer through wall into TEB. Before integration, TEB only considered heat transfer by conduction and two main boundary conditions, which are sensible and radiative heat flux. After integration, TEB can predict the evolution of capillary pressure into the wall, but also two new boundary conditions, which are wind-driven rain and latent exchanges. This new version of TEB has been evaluated by comparison with in-situ measurements. For this, we relied on in-situ instrumentation present in the medieval city center of Cahors, a small town in the south of France. A weather station is installed on a roof and provide local weather data. Several buildings are also instrumented. We will use the wall frame in red in the study and the room adjacent. To compare measurement and simulation, we have to configure tab to represent the district and this wall. For this, we simulate a very narrow street. Weather data or weather forcing is performed by using data from the weather station. The building is defined as unoccupied, and the wall properties are defined using agrothermal characterization of in-situ materials. Here we have the wall study. It is composed of 40 centimeters of bricks and internally insulated with agrothermal bio-based material, which is a mix of hemp and lime. The instrumentation, we have 3 places instrumented in the wall. We measure temperature and relative humidity at the interface and in the middle of the insulation. We only measure temperature at the indoor surface. Here we have an example of the comparison at the interface. The first graph represents the evolution of temperature, with in blue measurement and in black the result of tab simulation. The second graph represents the evolution of relative humidity. In both cases, we obtain a good agreement between measurement and simulation. Here we have a summary table with the result for all the variables studied. The mean absolute error is always about 1 degree and for temperature and lower than 3% for relative humidity. And the percent coefficient is always greater than 0.9, which highlights a good correlation between measurement and simulation. Therefore, this new version of tab seems to be suitable to the simulation of historical wall. Indoor conditions are also measured in the room adjacent and are compared with the result of tab simulation. The first graph represents the evolution of indoor temperature, with in blue measurement, in gray the results of tab before modification, and in black the result of tab including moisture transfer. Both versions of tab lead to a good agreement with measurement results. Therefore, taking into account moisture transfer seems to have almost no influence on the indoor temperature in this case. The second graph represents the indoor relative humidity. The modification made seems to have a greater impact here. Indeed, taking into account moisture transfer through wall help to regulate the indoor relative humidity and avoid peaks. Therefore, this new version of tab represents a significant improvement in indoor relative humidity simulation and is suitable for the simulation of indoor and all buildings. This new version of tab can also be used to study the impact of evaporative cooling on pedestrian comfort. The first stage consists in rain absorption by the wall. This is the wetting phase during which the relative humidity increases until 100%. This is followed by the drying phase, and moisture gradually evaporates. This leads to a low reduction of surface temperature. In this context, the impact of evaporative cooling potential on the outdoor comfort is negligible. Indeed, we study a very specific case with very narrow streets, and the walls intercept little driving rain, and the potential for evaporation is therefore very low. We also decided to study, we also add in the model a mold growth model. It can be used to evaluate the risk of mold growth. Here I will present just an example of what we can do with this implementation. We will compare 2 retrofit solutions. The first wall is made of brick and internally insulated with hemp and lime, a bio-based material and hygroscopic material. And the second one is internally insulated with expanded polystyrene, which is a more modern and impermeable material. This graph represents the evaluation of mold index, the evolution of mold index at the interface between brick and insulation for the most critical wall orientation over 4 years. There is a risk of mold growth when the mold index is greater than 3. In this case, only the wall insulated with polystyrene seems to present a risk. In conclusion, a numerical method for simulating hydrothermal transfer through wall on an urban scale has been developed, integrated into TED, and evaluated in the context of historical city center. We obtained a tool capable of simulating both conditions in the street, both conditions in the urban canyon and the energy behavior of the building, while considering moisture transfer through wall, and this on large spatiotemporal scales. In the future, this new version of TEP can be used to assess several retrofit scenarios based on energy and microclimate issues, but also on the durability of the wall. And it can also be used to study the impact of moisture transfer on an urban scale in different configurations and climates. Thank you for your attention.